Hello, and welcome to another segment of the Geology 1 Processes and Products Lab DVD. My name is Renee Clary, and today we will talk about groundwater. What defines groundwater? Well, groundwater simply means the water that is stored in underground rocks. Now, not all rocks store groundwater. If we look at a profile of groundwater, we see that in general there are two zones. We have an upper zone, the zone of aeration, where surface water, usually rain, will move through this zone through infiltration. The pores within this zone contain both water and air. There is a zone of saturation below the zone of aeration, and it is in this zone that the pores are filled with water. Now, the zone of saturation is separated from the zone of aeration by the water table. This is the surface that just separates the two. Now, if you need groundwater, if you need to drill or dig a well, you must be in the zone of saturation in order to withdraw water. The water table is not a static surface either. It generally follows the topography or the lay of the land, which means that in mountainous regions, the water table will be higher than it will be in valleys. Let's take a look at that in a diagram. Here we see a cross section. We have a zone of aeration here, and if we could take those sediments and look at them under a microscope and preserve the water that was within them, we'll see some of the blue stuff, the water, but also a lot of white or void space or air. This is the zone of aeration. Now, below the zone of aeration is our zone of saturation. And here, if we could preserve this material, and again look at it under a microscope, we would see that the pore space is completely filled with water. Note that the well is dug into the zone of saturation. This black line is the water table, or the surface which separates the zone of saturation from the zone of aeration. Now, what about rock types? Do all rocks store water? Absolutely not. There are aquifers which are very good at storing water, and there are aquicludes which prohibit water being transmitted through the rock. In order to be a good storage body for groundwater, a rock body must have a couple of good characteristics. One is porosity. There must be pore space or space between the clasts of the rock or between the sediments so that water can be stored. The other characteristic is permeability. If we have the water within the rock body, it's not going to help us if we can't get it out. So an aquifer, which is a body of rock that stores water, or a body of sediments that stores water, must have porosity or pore space, and it must also have permeability, or the ability of the rock body to transmit fluids. Let's look at this diagram to show you just some of the types of porosity. Here we have some rounded grains, and we do have pretty substantial water able to be stored in the pore space. Notice in this situation we have larger clasts, but we also have smaller clasts in between. Now, although some water can be stored, in general we can have a better aquifer if the grains are all the same size and they're rounded than if we have two different size grains. We can also have porosity because of dissolution or because of fractures within the rock. Groundwater moves from areas of high pressure to areas of low pressure, and it does move in broad looping curves. Although it only travels a few centimeters a day, it can be pretty fast in some areas, and it can be extremely slow in others. This is a neat little diagram because it shows us a nice little hill with a river channel at the bottom. Note that the water surface, the water table, is not straight across. Instead, the water table follows the topography or the lay of the land. It is of higher pressure here, where the water table is higher, and the water would then move in broad looping curves to an area of low pressure where the river is. Here we have the zone of aeration and the zone of saturation, and again, this black line is the surface which separates the two, or the water table. Now, how do we contour the water table surface? Well, it's very similar to a topographic map. First, we need to mark off the elevations where we have the water levels. Then we need to choose an appropriate contour, maybe 20 feet or perhaps a few meters. Now, once we have the topography lined out as far as the water table surface, we know that the flow of groundwater is going to be at right angles to our contour lines. Let's look at an example. Here we have a map with contour lines removed. We have some water bodies. There is a number here, 47 feet as the elevation of this lake. And we need to contour the water table. We can get some more elevations off of this accompanying map, and in order to save time, I've written a few in just to do that. Okay, so by pulling some of these elevations, these lake elevations, off of the previous map, we see that we have 47, 44, 39, and what I've decided to do, and have already sketched in a few lines, is to contour this at about a 5-foot interval. Well, let's start up here with a 45-foot contour line. And again, we're looking at water table, we're not looking at the topographic surface. So our 45 line is going to pass, it's just a little north of this little lake, which has 44. This one is 46, so we're going to have to drop down and move out. And we have a lake out here that's actually 45 as well. Now we need to do a 40 contour interval. Here's a 39 lake, so we're going to be just a little north of here. We're going to have to drop down and pass through this body of water, which does have 40 marked as its elevation. So this is our 40-foot contour. And we could take it down even farther and do 35. Here's a lake with 34. Bring this through. And I'm doing this fairly rapidly. You probably want to spend a little more time with it. There's a 35-foot. And we would continue on. We can definitely put a 50-foot in there as well. The flow of the groundwater is going to be at right angles to these contour lines, which means it's going to be in this direction. It's going to be at a perpendicular. Now, is it going to flow from 45 to 35 or from 35 to 45? Right. It's going to flow from the higher to the lower, from areas of high pressure to areas of low pressure. So according to my very rough contours, our groundwater would be flowing in this direction. If you need to get groundwater, generally you do so by digging or drilling into the zone of saturation. Now, sometimes digging or drilling into the zone of saturation produces an artesian well. Artesian means that the water moves up through the well under its own pressure. You don't have to pump it. And this is because the potentiometric surface, that's the level to which the water will rise in wells, is going to be greater or equal to the well. So the water will automatically rise up under its own pressure. The pressure builds so the water flows upward without ever having to be pumped. Let's look at a little diagram that can show us how this works. Here we have an aquifer. Remember, that has to have good porosity and good permeability, and it is storing some groundwater. However, because it is a confined aquifer, it looks like here we have a layer of shale above it so that the water cannot move upward. It is a trapped or confined aquifer. Our potentiometric surface, or the pressure surface to which the water would rise without having to be pumped, is shown along this dashed line. Now, what does that mean? That means if we drill into the zone of saturation, which would be down here in our aquifer, at this point, the level of the land is not equal or below that potentiometric surface. So we do have a well, but we're going to actively pump that well or draw water out of that well It's not an artesian system. However, look at this. What if we have a well in this little depression? Note our potentiometric surface is here and our land surface is below that. So if we drill into the zone of saturation, water will flow upward under its own pressure. This is an artesian system. Here's an old photograph of an artesian well in South Dakota in the early 1900s. Someone obviously dug into the zone of saturation and it was under pressure, and the potentiometric surface is much higher than the level of the land. Let's go ahead and try to see what would make where an artesian system would be in this diagram. And again, okay, what are we seeing in this diagram? Well, first off, we can notice that the brown lines are our contour lines. Over here we're going to have a hill because we can see that our contour lines are going to be increasing. We have 380 down to 370, 360, and 350. We also have some topographic contour lines that kind of move through the center in this fashion. And these blue dashed lines, on the other hand, are going to represent our water pressure surface. This is the potentiometric surface. You can see I've kind of pre-marked some of these dots. So what we're looking at is where the potentiometric surface is going to intersect with our topographic contours. Okay, let's mark those dots. Where the 370 contour intersects with the potentiometric surface, we're going to mark that down. Here's another one. Okay. Then we can take the 360 potentiometric surface contour, the water pressure surface, and see where it intersects with those topographic contours. Let's see, anywhere else? Yep, right here. Okay. We can move down now. Okay, that is the 350. And one over here. 340. Oh, there's the 340 contour there and there. Again, we're marking intersection points. When we drop down to 330, there's the contour line at 330. We intersect with the water pressure surface at those 2 points. And although it's not marked, we know that that contour interval, we know our contour interval is 10 feet, so that has to be 320 right here. There we go. Intersecting with our water pressure surface. Next, I'm going to basically connect the dots, but in a nice, even fashion. Whoops, I think I've goofed there. Let's check. Yeah, that dot doesn't belong. I made a mistake when I put that one in. There we go. Let's ignore that one. That's a goof. Okay, now we have our diagram divided into two different parts basically. Let me go ahead and shade in some for you. Now below the black lines, what we're going to be seeing is that the topography is always going to be higher than the water pressure surface. We are never going to be able to drill into these areas and see a place where the water will automatically rise up. However, let's go between those two black lines, and you see that the water pressure surface is always going to be greater. Okay. Right here, if we're on the 370 water pressure surface, it intersects that contour at 360, so if we drill a well there, water will rise on its own. And in fact, all of this area that I'm going to shade in for you represents that area in which we can drill into the subsurface, and the water level will rise under its own pressure. Why do we study groundwater? Well, it's the third largest water source. Of course, that's way after glaciers, and of course the number one water source is that of oceans, but it's the most important source of fresh water. Groundwater is a geologic agent, which means that it changes the Earth's surface through erosion, transportation, and deposition. Let's look at some of the ways that groundwater can erode. As groundwater moves through existing rocks, it can dissolve and create pore spaces, especially in limestone. It can form caves, sinkholes, and when dissolution proceeds to a fairly advanced state, we get something known as karst topography. Here we see a cross-section where we have the water table currently shown at the dashed line, but it seems that at some point in the past the land was actually lower or the water table was higher, because we have a lot of caves that were dissolved out of the limestone. Note that if we look at the little circle showing us a cave system, we also see some cave features. Groundwater produces these as well through deposition. As the groundwater percolates through, it will deposit its mineral content as it reaches this air. Basically, it's supersaturated at that point, and the minerals come out of solution. We can end up with stalactites that form from the ceiling from the dripping water. The stalagmites grow from the ground underneath the dripping water, and over much time, if the two actually meet, we have a column. Here's a photograph of a cave. You can see the stalactites. Here we have a big stalagmite. No good column. Okay. Not only will caves form, but sometimes the overburden of structures on top of the cave will cause the top of the cave roof to fall. And in this case, where we have depressions formed, we refer to them as sinkholes. This is in Florida in 1991. Can you imagine the surprise as the person drove home to find their home had been swallowed up in a hole, a sinkhole? And here are some sinkholes that caused a little bit less damage. They are in an area where there are no houses, and they've since filled up with water. Now, karst topography will form when we have dissolution to a more advanced state. We have caves and sinkholes in the area, but we also have underground rivers, where rivers will suddenly disappear from the top surface and then flow underground for a while. Dry valleys, where rivers once flowed and no longer flow. Here we see a stage diagram of karst development. In the early stages, you can see some dissolution in the cross-section that we're dissolving out our limestone here. We have a stream, some springs, a couple of little depressions that might be sinkholes. When we get to an intermediate stage, we see here that our stream is disappearing on us. It's probably moving underground at that point. A lot more of the sinkholes, a lot more dissolution. And in an advanced state, we have few streams. We have these things called solution valleys that have basically been formed by hooking together a bunch of sinkholes. This is where the river once flowed, but now, because of collapse of the overlying rock layers, we have a valley structure. This is a solution valley. You see, we still have some more sinkholes. We have disappearing streams moving along, and all of a sudden it disappears. It continues its route in the subsurface. Here's an overhead photograph of karst topography underlying limestone rocks. You can see the sinkhole. You can also see how the topography is very rolling. There are some nice little elevated areas that are more resistant, and we see some sinkholes from collapse. Karst topography on a topographic map can be pretty easily spotted because of the sinkholes, because you do see that rolling topography. You see areas of uplift, little hills, and you also see those sinkholes. You can oftentimes pick out some of these disappearing streams. There will be a segment of a stream that's flowing along, and then all of a sudden it terminates. And chances are, if you also see these little lakes that are representative of the sinkholes, as well as the nice rolling hills, you're looking at a system where you have karst and the stream disappears underground and continues on in the subsurface. Let's take a look of an example there. Okay. Here is an area in Kentucky, Mammoth Cave, Kentucky, and I guess our first clue that it is a karst area is that we do see lots of little sort of rounded features with our contour lines. We do have sort of a rolling topography, but on a very small scale. We have little hills and we have valleys. We see little bodies of water here. They're small on the map. There's another one here. There's several little ones down here. These are all sinkholes that have subsequently filled up with water. Now we can also spot some disappearing streams. Let's see if we can find one. Let's see. We have, let's see, Sinking Creek over here. If you follow this along, we have a nice little stream. And then all of a sudden it's dashed. It's gone underground. And it's actually flowing along now in the subsurface. The little lines become dashed. Solution valleys, here we have another Sinking Creek again. Well, this one's actually Little Sinking Creek, sorry about that. And this one is Sinking Creek. And this guy, if you look at him and you're able to examine the contour lines, you can see that Sinking Creek sits in an area of pretty low elevation. And judging by these little sinkholes, and there are numerous sinkholes down here, this is probably one of the solution valleys. Okay, geologic agents are important because they change the surface of the earth, and groundwater, like all of the other geologic agents we discussed this semester, erodes, transports, and it deposits. Now, we've looked at a few of the ways it erodes already. We talked about caves and dissolution, and we've looked at sinkholes, and we've also talked about karst topography. All of those features are dissolution features. We've eroded. Groundwater doesn't transport big pieces. It doesn't transport sand. It doesn't transport gravel. Glaciers do. Rivers do. Groundwater, however, is moving through pore spaces. So the only way that it's really transporting is in solution. But it's very important as it transports minerals in solution because it's one of the main agents for lithification or cementation of those sedimentary rocks that are the most popular type of rocks on the Earth's surface. All geologic agents erode, transport, in this case we're looking at minerals in solution, and deposits. Groundwater precipitates in pore spaces, and again, it's one of the main agents of lithification. And as you probably recall, lithification is the process of forming sedimentary rocks. Now, what are the problems that are currently associated with the groundwater state of affairs in our country? Well, we can end up with problems if the water table is lowered. And that happens when water is pumped out faster than it can be naturally replenished. Now, groundwater can be replenished, but the problem is we, as humans, pump it out often much, much faster than it's naturally replenished. In that case, we can kind of think of groundwater as a mineral of which we mine. So we're taking it out faster, and we are slowly lowering the water table. Now, if we take out water and we're in substrate where the sediments are fairly loosely packed, we can end up with subsidence. And this happens when the water's pumped out and the ground basically dries out and compacts and the land is lowered. Here you see what happens. Here is our initial water table level. And because a lot of pumping has been done, this is the present water level, so we call the difference the overdraft. Water is removed faster than how fast it could have been replenished. This is a really striking photograph. This gentleman down here for scale is showing us what happened in the San Joaquin Valley in California because of groundwater extraction. Up here on this post is the year 1925. In 1925, that was the level of land in the San Joaquin Valley. But because of intense irrigating practices and intense farming, the land has subsided to the location of the man in 1977. Subsidence can be a serious problem. And finally, the groundwater problem that many communities encounter is that of pollution. Essentially, if you dump it, you drink it. Although you may think the motor oil in the backyard is an easy way to dispose of something you don't want, remember it doesn't just stay there and not interact with the environment. It will infiltrate down through that zone of aeration and eventually hit that zone of saturation. Although you may not drink the motor oil, somebody eventually may. Pollution can occur from septic tanks, solid waste facilities, and underground storage tanks, USTs. When they're leaky, we refer to them as LUSTs, LUSTs. And here we see some sources of potential pollution for groundwater. Crop dusting. There's a lot of runoff of this pesticide, and that will end up in river systems, perhaps groundwater systems. Here we have just domestic trash waste that has been deposited right in a body of water. That's not a good idea. Again, it doesn't stay there and not interact with the environment. It interacts with the environment, and it will affect our groundwater. Here we see a lot of animal waste. Again, we're going to have runoff from this form. It will find its way into streams. It will affect our groundwater quality. And industrial waste, chemical waste. Although these barrels may have seemed like a good idea at the time, they do rust, and eventually the chemicals can breach out of their containers. And it will infiltrate through the zone of aeration and may eventually find its way to our groundwater system. Well, that concludes our discussion today of groundwater. If you have any questions with any of the lab exercises or with any of the material, please feel free to email your instructor. He or she will be happy to help you and to answer your questions. Thank you for joining me, and have a great day.